today's class, we will quickly learn about half-wave and full-wave rectification. So first the question comes in our mind is then what is rectification? Rectification is a process by which a full cycle AC waveform is converted into single polarity half cycles. So it's not a conversion process of AC signal to DC signal. Rather, it's a conversion process of AC waveform, means a full cycle waveform, into a single polarity half cycle. So it will be either positive half cycles or it will be a negative half cycles. Now in this figure, what we can see here, we have a full cycle sinusoidal signal where it has positive half cycle and negative half cycle. Now between 0 to capital T, this is the total time period of that full cycle. So for each cycle, be it positive or negative cycle, the time period is half of that. That means T by 2. So from 0 to capital T by 2, this is the time period for positive half cycle. And from T by 2 to capital T, it's time period for negative half cycle. Now Vi here represents the instantaneous value of the input signal or input waveform, where capital V suffix M is the peak value of that input voltage. Now when this AC signal passes through a converter circuit, now after conversion, what we can see here that the positive half cycle remains positive, but the negative half cycle changes to positive half cycle. Now here again, for each half cycle, the time period is T by 2. So between 0 to capital T by 2, again we have positive half cycle, and between capital T by 2 to T, we have again another positive half cycle that has been converted from negative half cycle. And here V0 represents the instantaneous output voltage, where again capital V suffix M represents the peak or maximum value of that voltage signal. Now this is one kind of conversion process. Now we have another kind of conversion process where you can see that again as input we have full sinusoidal signal or waveform where we have positive and negative both the cycles, and when it passes through a rectifier circuit, the positive half cycle remains positive but the negative half cycle vanishes. The value of that output signal is 0. And from 0 to this is T, this represents the complete cycle, and after T the process gets repeated. So for positive half cycle it remains same, and for negative half cycle it vanishes in case of output. So this conversion process is about AC full cycle waveform to single polarity half cycles. So this is not exactly the conversion process from AC to DC, as I said. An AC signal gets converted to DC by rectification first and then followed by filtering. And this filtering process normally happens by involving the use of a large reservoir capacitor, which charges to the peak input voltage level to produce the DC output and discharges partially, which results ripple voltage on the output. And then this ripple can be further reduced by using filters like RC filter or LC filters, but this filtering process is not within the scope of this class. I will discuss about this conversion process from AC to DC involving filtering in my future class. So let's focus on the rectification part only for today's class. So the circuit which is responsible for this rectification process is called rectifier, and we have broadly two types of rectifiers: half-wave rectifier and full-wave rectifier. Now we will throw a little bit more light on this classification, half-wave and full-wave rectification. So let's talk about half-wave rectifier first. The process of removing one half of the input signal to establish a DC level is called half-wave rectification. That means for the full cycle input signal, in the output we'll be getting either the positive cycles or the negative cycles, and the other part will vanish in the output. Now next we will see the rectifier circuit, or rather half-wave rectifier circuit, that involves a diode, because the unidirectional property of a PN junction diode will be using there. And we have two types of half-wave rectifiers, positive and negative half-wave rectifier. In case of positive half-wave rectifier, in the output we will be having all the positive half cycles, and for the negative half cycle part of the input signal, in the output we will have 0 value. Similarly, in case of negative half-wave rectifier, we will be having only the negative half cycles. But generally, when we talk about half-wave rectifier, we use a circuit where we get only positive half cycles in the output. That means positive half-wave rectifier. Now in this circuit, what we can see is we have a transformer here, and the nature of the transformer is step down, and this is the supply voltage, AC supply voltage definitely, and that will have a higher value that is not required for conduction of a diode or for operating this rectifier circuit. So definitely we will be stepping down the voltage level, and for that purpose we are using the step down transformer here. And on the other side, what we have in the rectifier or half-wave rectifier circuit, we have the main part here, main component, which is diode, PN junction diode. And here at the output side, we have a resistor, which is called here a load resistor. Now, when the input signal is in its positive half cycle, so this will be positive and this will be say negative. So after stepping down the voltage level, the polarity will remain same. So at the input side of the rectifier circuit, the polarity of the input signal will be this is positive and this is negative. Now what will happen? So when the input signal is in its positive half cycle, so again the representations and their meaning are same. So what will happen is the diode, since this is the P side and this is the N side, so P side is getting connected with the positive terminal of the voltage or input voltage. So this diode will act as a forward bias diode. So that will be turned on. So when the diode will be on, so the circuit will be a closed circuit and a current will flow in this direction. Let's say that current is IL, and that will flow in this direction through the load, and after flowing through the load it will come back this way. So this will be the complete path. Now since for the positive half cycle the diode is getting conducted, current is flowing through the load, so as the current is flowing through the load, so there will be a voltage which will be dropped across that load resistor, and that we are representing by V naught. This is the, as I said, instantaneous value of the output voltage. Nature wise the output signal will remain same, so it will be sinusoidal in nature. So for the positive half cycle we will be getting again a positive half cycle in the output. And what will the peak value of that sinusoidal wave? Ideally the voltage drop across this load will be the voltage as we are applying as input minus the voltage drop across this diode. If we apply KVL, then the input voltage will be equal to the summation of the voltage drops across this diode and across this load. So the voltage drop across this load will be input voltage minus the voltage drop across this diode. But with respect to this input voltage or the voltage drop across the load resistor, the voltage drop across the diode will be very negligible. That's why the peak voltage or the maximum voltage across the load resistor is taken as same as the peak value of the input signal, and that's why it has been shown by V suffix M. So this is the practical scenario. Now when the input signal changes its polarity, means from positive half cycle to when it goes to the negative side, then this side becomes positive and this side becomes negative. And since the polarity remains same, so at the input side of this rectifier circuit also this will be plus and this will be minus. So current will try to flow in this direction through the load, and this way it will come here. But since this is the negative side or N side of the PN junction diode, and which is connected to the P side or positive side of the input voltage, so that means the diode will act as a reverse bias diode, and this time the diode will not conduct, it will act as open circuit. And since this circuit, rectifier circuit, will work as open circuit, so no current will be flowing through the load. And since no current will be flowing through the load, so voltage drop we know as per Ohm's law, that is the current flowing through that particular resistor or load multiplied by the resistance value. So current is 0, that means the voltage drop across the load will be also 0, and that's why in the output waveform also the voltage drop across that load resistor is 0. And again when this input signal from negative half cycle to when it will move to the positive half cycle, again this PN junction will act as forward bias diode, and again the same process will be repeated. So this is how the half wave rectification happens. So far I have talked about positive half wave rectifier. Now I am leaving this on you, that how the position of this diode in this circuit will be changed so that we will be getting only the negative half cycles in the output, and all the positive half cycles in the output will have zero value or it will be off. So think on it. Now we'll move to full wave rectifier circuit, means full wave rectification. So this is a process where positive half cycles will remain positive in the output and the negative half cycles of the input signal or waveform will be also converted to positive half cycles, and in the output we'll be getting all the positive half cycles. So this is what we understand by full wave rectification. Now again in this circuit what we can see, we have a transformer, and definitely this is again a step down transformer. We have at the input side of that transformer a AC signal, and the value and the amplitude of that voltage signal will be reduced through this transformer action, and at the secondary coil, at the secondary side of this transformer, will be getting a reduced voltage that can be tolerated by this rectifier circuit or these diodes. Now in case of full wave rectification, we generally use two types of circuits. One is called center tapped rectifier circuit, the one which we are using here, and bridge rectifier circuit, the one that we will be discussing about in our next class. Now why it is center tapped? Because at the secondary side, the coil that we have, as you can see, the conductor that we have, this is basically at the midpoint or center point of that secondary coil. Now in this center tap full wave rectifier circuit, instead of having one diode, here we have two diodes, and again we have a load resistor across which we will be measuring the output voltage. Now suppose when we are applying AC signal at the input side and when it is at its positive half cycle, then that will be reduced to some other value, but the polarity will remain same. So the potential of this point will be at higher level compared to the potential of this point and also the center point. Now when that will happen, then the positive side of that PN junction diode will be connected with the positive side of that input signal. So the diode will act as forward bias diode and it will be turned on. So it will be a closed circuit through this load resistor till this center point or midpoint of the secondary coil. So the current will flow in this direction through the load resistor, then it will come here and then it will be flowing this way. Let's understand this by the help of waveforms. Now this is the input waveform where we have full cycle. Again the time period is same, and for positive half cycle it is T by 2, for negative half cycle also it is T by 2, their peak values are same. So in case of positive half cycle of the input signal, as the diode is getting conducted, current is flowing through this load resistor, so we will be getting a non-zero value of voltage drop across this load resistor. Now as I said that the voltage drop across a PN junction diode will be very negligible compared to other voltages in this rectifier circuit. So the input voltage that we are getting here, that will be dropped, the same voltage will be dropped across this load resistor, and that's why the peak value has been shown by Vm. But during positive half cycle of the input signal, since this point is at lower potential compared to the center point, so the P side of this PN junction diode will be connected with the negative terminal of this input. So this diode 2 will act as a reverse bias diode, and this diode will be turned off and no current will be flowing through this diode. Now let's see what happens during the negative half cycle of this input waveform. So if we consider the first diode, then the P side of this diode is connected with the negative terminal of the voltage. So diode 1 will be turned off, so no current will be flowing through this diode. But what about diode 2? Diode 2 P side of this PN junction diode will be connected with the positive terminal. So diode 2 in that case will be turned on. A current will start flowing through this diode, and this way it will flow through the load resistor and it will complete its path. So through this closed path a current will flow, and again a voltage will be dropped, a non-zero voltage will be dropped across this load resistor. And during the positive half cycle of the input signal also, if you remember, then the flow of current was in this direction. That means, so during the positive half cycle, the polarity of this V0, the voltage drop across RL, was positive and this was negative. That means in both the cases, in both the cycles of the input signal, the polarity of the output voltage is same, and that's why in the output waveform this has been shown by the same polarity half cycles. Next, we will talk about a few important parameters associated with half-wave rectifier and full-wave rectifier. The first one is average value. Average value for an AC signal is calculated over a single time period, means from 0 to capital T, and we calculate the total area covered by that waveform. So during positive half cycle, the time period is 0 to T by 2, and that was the expression of the voltage signal Vm sin omega t that we know, and that has been integrated with respect to time. But during negative half cycle, for a half wave rectifier, at the output side the voltage value is 0, and that's why the total integration is over 0 to T by 2 only, instead of 0 to T in case of half wave rectifier. But since this is average value, that's why we are dividing that total area by the total time period, which is capital T, and after calculating, after simplifying this, we will be getting a value Vm by pi. Now in case of full wave rectifier, the concept is same, the formula is same. So this is again the total area covered by those two half cycles over a time period, which is capital T. So this time this integration is between 0 to T, and again the voltage signal, the expression of that output signal Vm sin omega t, and we are doing this integration with respect to time, and again the total value we are dividing by the total time period, since we are finding here the average voltage, and after evaluating this integration, finally the value that we will be getting for full wave rectifier is 2 Vm by pi as average value. The next important parameter that we come across for rectifiers is RMS value, and again this is associated with alternating signal only. This is the formula, and again the concept is same as during negative half cycle of the input signal, at the output side the voltage value is 0. That's why the integration is again over 0 to T by 2 instead of 0 to T, and we are finding the mean value. So we are dividing by the total time period T here, and then finally we are taking the square value, and after evaluating this integration, final value we will be getting for half wave rectifier is Vm by 2 as the RMS value of that output voltage. Now in case of full wave rectifier, the only difference is that integration is over 0 to T, and finally after evaluating this integration we will be getting this value Vm by root 2, which is the RMS value for an AC signal. Now the next parameter is ripple factor, and this is the formula for half wave as well as full wave rectifier, and since the average value and RMS value are different for half wave and full wave rectifiers, that's why their ripple factor values also are different. For half wave rectifier it's 1.21, and for full wave rectifier is 0.482. And the next important parameter is efficiency of the rectifier circuit, and for efficiency this is the formula, and for half wave rectifier the efficiency is 40.6% when we take the resistance of the forward bias diode is 0. Now if we put 0 in place of RF, so this part will vanish and the denominator will be 1 in that case. That means in the formula this much will remain. Now if we put the corresponding value of V average and V RMS for half wave rectifier, then finally the value we will be getting is 40.6%. Now the same thing is applicable for full wave rectifier also. It has its own average and RMS value, and also we are assuming that the resistance of forward bias diode is 0, and this time the efficiency is 81.2. That means the efficiency of a full wave rectifier circuit is twice the efficiency of the half wave rectifier circuit. Now this is a comparative study of all the important parameters for half wave rectifier, full wave rectifier of center tap type, and full wave rectifier of bridge type, which we will be seeing in the next class. So this much is for today. Stay tuned for such videos. Thank you.